What's up, mathematicians? Justin here, and today I'd like to talk about measurement and intuition. Okay, so I'd like to start off by proposing a couple of measurement problems to you. The first one I'm going to call the band around the world. Okay, so these are measurement problems. And number one, calling the band around the world. Okay, so in order to visualize this, let's start by drawing a circle rather. I'm going to use my compass for that. If you don't have a compass, it's okay. You can freehand draw it. You will need a compass when we get to proper construction. So if you don't have one, I recommend getting one. And first of all, let's pick the middle point for this circle here. I'm going to center it right there. Okay, just making sure I have space there. Okay, so I'm going to start by drawing this circle on the paper. Now, while my compass is still centered at this point, I'm going to draw a slightly larger circle. So I'll have one circle inside a slightly larger circle. All right, there are my two circles. And I always find it so satisfying to draw a circle with a compass. They come out so beautifully. Now I want you to imagine that this inner circle is the Earth, but we'll say it's an idealized version of the Earth. It's a perfect sphere, perfectly circular. The Earth itself is actually not a perfect sphere. It's wider at the equator than it is, at the poles. And it has bumps on it, right? It has all these mountains and valleys and things like that. So it's not a perfect smooth sphere. So we're just going to pretend it's a perfect smooth sphere. And that we have put a metal band around it, touching it, maybe around the equator, basically the largest possible metal band that could be put around the world, touching it all around the world, so snug against the planet. Okay, so the approximate circumference of the Earth is 40 million meters, 40,000 kilometers. That's approximate. We're just going to go with that. So 40 million meters. So this metal band that is touching the Earth all around the equator is 40 million meters long. It's pretty long, piece of metal. But now, just for kicks, let's say someone decided to go cut the band and pull it and add a segment to it. And we'll say that they added a 4-meter segment. So they have made it longer by 1/1,000,000th of its circumference. And after they've made it, longer, then it's now hovering just a little bit above the Earth, all around the Earth. And so now this newly expanded band, the outer band that we see here, is not 40 million meters long, but it's 40,000,004 meters long. And the question here is, what is the distance between the newly expanded band and the surface of the Earth, assuming it's floating just above the Earth, all around the Earth, perfectly circular, perfectly rigid? This is a mathematically idealized situation, which obviously would never exist in reality, but we can still imagine it in our heads. We can still, we can still picture what this would look like. And so the question is, what is that value of x? What is the distance between the Earth and the band that has now just been increased in size, in circumference, by 1/1,000,000th of its original length? by someone who just added a 4-meter segment into the band. That's the first question. Okay. Now let's look at the second question before we actually solve either of these. I want to pose both of them to you. All right, the second question is this. Imagine that, let's call it the metal rod, the mile-long metal rod problem. So imagine that you have a metal rod and it's a mile long. And 2, 4, 6, 8, 10. We'll call this the middle. 2, 4, 6, 8, 10. Okay. So I'll draw it across here. So this is my mile-long metal rod. Or no, actually that's not my mile-long metal rod. So the idea here is that you have a metal rod, it's a mile long, okay? But in the middle of it, it has a hinge. And from one end is fixed, and from the other end, you push it 1 inch over. Just 1 inch, not very far, right? So one end is fixed, the other end gets pushed in just by 1 inch. Perfectly rigid, so it buckles up at the hinge. And so in the middle where the hinge is, the rod is now above the ground some distance. And so let's go ahead and draw, what that looks like here. Okay, so this distance here is now no longer a mile, right? It is 1 inch shorter than a mile. So I will say 1 mile minus 1 inch. Okay, and then of course this length here is a half mile. And this length here is also a half mile because that hinge was right in the middle of the metal rod, mile-long metal rod. Okay, so similar to the previous one, what we want to know is what is this distance right here? We're going to call that x. What is the height that the center of this rod, where the hinge is now above the ground? So those are the two questions, two measurement problems, both of them trying to find, some distance after some modification to some, weird, maybe contrived, unrealistic situation. Mathematical situations, not anything that would happen exactly in real life. But you can see how, especially with this one, there could be some practical applications for this. It comes up sometimes looking at issues around railroads and things like that. Okay, so now let's think about, how should I put this? I want you to consider the following. And let me pull this up real quick. Okay, so here. So for each of these situations, the band around the Earth and the mile-long metal rod, I want you to think about that gap and ask yourself intuitively, and this is before you actually solve the problem, right? Intuitively, think about that gap. Is it thick enough to slide a piece of paper underneath? Do you think it's big enough for an ant to crawl underneath? Do you think a mouse could crawl underneath, or a cat? Do you think you could crawl underneath in that gap between the metal rod or metal band and the ground? And finally, do you think a full-sized African elephant could walk underneath without having to bend down? So think about those questions intuitively. And let's come back here to this screen. So looking at these situations, think about it intuitively. The thickness of those, the X for this one and the X for this one, which one of those categories does it fall under? Like Can a paper go under, a piece of paper go under it? A mouse, you, an elephant? Just make a guess, an intuitive guess. And then once you've made your intuitive guess, I encourage you to actually do some computation and try to figure it out on your own. What is that distance? We will do it together in just a minute, but pause the video, try to do it on your own first. I really recommend that you try that. Okay, let's look at the band around the Earth problem first. And I'm going to draw in a couple of radii. So first I'll draw in a radius from the middle to the Earth, the edge, like the surface of the Earth, and then a second radii from the middle to where the band is. I'll call this radii R1, and I'll call this radii R2. And now, in order to find this distance x, it's just the difference between R1 and R2. Well, the formula for circumference is equal to 2 pi r. Well, what that means is that if you want to know what the radius is, then radius is just equal to circumference. Oops, let me write it differently here. The radius is equal to the circumference divided by 2 pi. So let's use this formula right here to figure out these two radii. So first of all, we have R1 is equal to the circumference, which is 40 million meters, divided by 2 pi. All right, now the second radius, R2, is equal to 40 million and 4 divided by 2 pi. But since this is just 40 million plus 4, I could rewrite this fraction as R2 is equal to 40 million divided by 2 pi plus 4 divided by 2 pi. Okay, well now look at what I have right here. 40 million divided by 2 pi. That's the same as radius 1. So let's just plug radius 1 in here in place of this. So now I can see that, okay, R2, the longer radius, is equal to R1 plus 4 divided by 2 pi. Well, okay, let's subtract R1 from both sides, and that leads us to the following equation, that R2 minus R1 is equal to 4 divided by 2 pi. Let's go ahead and plug this in to the calculator and see what I get. So 4 divided by, put in parentheses to make sure, 2 pi, and I get 0.636. So this is approximately equal to 64 centimeters. Okay, so thinking about what I asked you, is this enough for a piece of paper to slide under? Definitely. Could a mouse go under there? A cat? Absolutely. Could you squeeze down 64 centimeters? Down to a gap 64 centimeters high. It's a little more than half a meter. I bet you could. Could an elephant? No, definitely not. An elephant's not going to squeeze under a 64 centimeter space. But there's a good chance you find this pretty surprising. Most people do. Most people think it's going to be a very thin, maybe a sheet of paper, maybe an ant goes under, but not very tall. Nothing that a human would be able to go under. So one other thing that's really interesting and counterintuitive about this problem is that it doesn't matter how large the spherical object is. You could do the same thing to a basketball, for example. Take a basketball with a metal rod, snugly around it, and add 4 meters, and guess what the gap between the basketball and the rod would be? 64 centimeters. You could do it to what's a bigger sphere? I don't know. A big beach ball, maybe like one of those really big beach balls. Do it to a large beach ball, and it's going to be the same, 64 centimeters. If you add 4 meters, it's going to be a 64 centimeter gap. You could do it to the Earth, as we discussed. You'll get a 64 centimeter gap. You could do it to the sun. You could do it to a sphere the size of the universe. And just adding 4 meters to that band will always yield a 64 centimeter gap, no matter how small, the size of a marble, or how large, the size of a planet, or even larger. The gap is always the same if you add 4 meters, which is counterintuitive. Most people are surprised by that fact, but we can see here, based on the calculations, it's true. Let's go on to the next one. Okay, so now we have a mile-long metal rod, and this one we can actually use a little trigonometry to solve. If you know the Pythagorean theorem, you can use the Pythagorean theorem as well. But let's use trigonometry because we haven't looked at the Pythagorean theorem yet in this course. So let's go ahead and break it down to inches. I find it easier to solve this problem if we break it down to inches. So first of all, how many feet are in a mile? That's 5,280. And we'll multiply that by 12. So in a mile, there's 63,360 inches. Let's divide that by 2, and I get 31,680. So this half a mile is equal to 31,680. Okay, and then of course this distance here across the bottom of the triangle, this is a right triangle we're finding the height of, is ½ an inch shorter than that. So let's try to find this angle right here. We'll call that theta. I can't really even fit a theta in there, but I'll write it here. So we'll call that right there theta. Okay, so since we're dealing with we don't know the height, we're dealing with the adjacent and the hypotenuse, we're going to say that the cosine of theta is equal to the adjacent, which is 31,679.5 along the bottom, over the hypotenuse, which is 31,680. So in order to find the angle, I'm going to need to use the inverse cosine. So second cosine, and we'll say 31,679.5 divided by 31,680. And I'm left with this, 0.321907. Okay, so I'm going to try to hold on to a lot of those significant digits because if this answer is really small, I want it to be as precise as possible. I'll write here that theta is equal to 0.3219 degrees, but I'll keep even more significant digits in my calculator. Okay, now that I know theta, I can use the sine function, right? Because I want to find x. So we're going to say that the sine of theta is equal to x over the hypotenuse, so 31,680. In order to get x by itself, I can multiply both sides by 31,680. So these cancel out, and I get that x is equal to 31,680 times the sine of theta, theta being this 0.3219, on and on. All right, so let's go ahead and plug that in. 31,680 times the sine, and I'm going to hit second answer because that's going to pull back my angle from the last one, and I get 177.98. So I think I can round to the nearest inch in this case, so 178. So x is equal to 178 inches. Okay, that seems like a lot of inches. But thinking back to the question, you know, how large of a gap is that? What could fit underneath there? Let's divide this by 12 to get the number of feet. And we get 14.8. Okay, so for most people, this is another surprising result. 14.8 feet. Okay, so in other words, you know, you would have no problem not just crawling through, but running and jumping through. 14.8 feet is pretty high. And an African elephant, a full-size African elephant, would have no problem just walking underneath this gap. Typical African elephant height, full-grown height, would be maybe around 10 feet tall. And so we're talking about a pretty sizable gap here, which again, most people find pretty surprising, since we only shortened the distance across the ground by one inch. We pushed that metal rod in by 1 inch, and it buckles and raises the middle so high that an elephant could easily walk under that gap. Kind of surprising. So what I'd like you to take from this is that in contexts involving measurement, we often sort of use our intuition about things, and we've talked about some of the assumptions that we're making about things like proportionality that seem right to us. But we have to be careful, because sometimes things that seem right, that seem intuitive to us, are wrong. We can't just depend on our intuition. And it's possible, I guess, it's possible that you had the right intuitions about these situations, that, you know, this would be something that would be big enough and wouldn't depend on the size of the sphere, and about how high this would come up. Maybe you did have a better intuition than most people, but most people have, you know, their intuitions are pretty wrong about these things. So, okay, maybe yours was right, but how do we know that your intuition is right about other measurement related activities when, you know, and right about these? You can't necessarily be certain that your intuition is going to be right about all measurement related situations. So we're going to leave it there. In the next video, we're going to talk a little bit more about the assumptions and you know, some of the potential problems and how we might start to think about how we might overcome those. So I hope to see you then.